Our next speaker is Mircea Trif from Institute of Physics, Polish Academy of Science, and he's going to tell us about cavity magnonics with domain walls and insulating ferromagnetic wires. So let's give him a big hand.
Yeah, thank you, and thanks the organizers for giving me the opportunity to teach to you this work that is not yet published, but it will appear very soon, which was done together with Jaroslav at UCLA. And yeah, just to kind of, I realized that at the beginning of the workshop that MacTop is a very similar kind of institute, like PCS. So it's the same kind of structure, team leaders and all of that. And just to mention, like the trivia, today we have a deadline for extending our institute. After the talk, I will take care sometimes. So my work is also related to what Jizu was discussing yesterday about about qubits encoded in domain worlds. And in particular, that's kind of my main message in a nutshell. Trying to find ways to see some quantum effects in these domain worlds, which is at the core of using domain worlds as something quantum. So that's kind of in a nutshell what I'm going to talk today about: a domain wall cavity between -L and L, far away from the edges, which can be scrutinized with some microwave power. The domain wall, as Jizu was demonstrating, harbors some energy levels that typically are not equidistant. And what we want to show that one can go from some boring level structure, thermal level structure, nothing quantum. You still have levels, but there is nothing quantum. By using magnons, we can show that theoretically you can do some ground state cooling that is necessary for any qubit initialization, and even create some kind of quantum states, which I will define what do I mean by that. So that's my outline, motivation, and we had some very extremely interesting previous two talks on the motivations, on usually using topological defects, magnetic topological defects for any kind of information processing, not quantum. Then I will brush a bit on how to quantize the domain wall motion, but we talked already quite a bit about that, so I will not stay too long, but I will extend some aspects that he was discussing. And finally, I'll show that we get some interaction between domain wall and spin waves that can be harnessed to manipulate and probe the domain wall quantum level. So that's kind of the typical slide one starts. So how it all started with this racetrack memory that in principle, that we saw there are not many yet actual application, but at least in principle could be utilized for information processing. Of course, these are metallic ferromagnets. What I'm concerned today is insulating ferromagnets. Size is hundreds of nanometers. You can measure the tunnel magnetic resistance in order to read out these states and so on and so forth. And what I want to see, but first, if we can use the domain to do quantum information processing, and that's what Jizu was talking about, that you can consider the quantum regime where these domain walls harbor some levels. And more importantly, before doing any quantum information processing, the question is, do you see any quantum effects? I mean, that would be kind of the natural question, right? In a way, right? So I think it's very nice to do some quantum information processing, but first we need to demonstrate quantum effects. And there were already quite a few proposals that look into that. And I think, to the best of my knowledge, that Sotake and Masoud Mohsen at Google, they had this very nice proposal to use antiferromagnets on top of the ferromagnet, and you can manipulate. First, they define some level structure there. I will show you in a bit, and you can manipulate the level structure with microwaves. Zizou, as he discusses today, showed that you can even have flying qubits, and you can manipulate this by moving the domain wall in a real space. And also, Christina Zarudaki, collaborator, had recently a paper that received quite a lot of attention, much more than what So was receiving, on encoding quantum information in insulating magnets that harbor skyrmion. So how are these defined? So usually qubit is defined in the low energy sector of the topological defects, insulating magnets. 2 qubit gates, single qubit gates, you apply some magnetic pulses on these objects and you can rotate them, or as you was mentioning, you can move them around. 2 qubit gates enabled by local tunneling. You can bring them in proximity, either here, as you was already saying. And because these are the low energy modes of the system, here they disregard any kind of magnons or that are kind of natural in the system. So how, why using this topological defect? So what do you need for qubits? Usually, if you want to use magnons for anything, magnons are pretty harmonic, right? While this topological defect is soft modes associated with domain walls or skyrmions, you can deform them a lot, so they exhibit a highly nonlinear level structure, which is necessary condition for doing some qubit implementation. So you can really manipulate the level structure. It exhibits very equidistant level structure. So that's kind of the reason. And also it's well separated from the other excited states. So that's kind of one argument for utilizing.
Sorry.
Yeah.
May I ask just curious about the picture spectrum?
I have to go back.
There is some kind of, I don't know, fine structure of E4 energy level. Maybe you could comment on it.
Yeah, so I didn't, here, for example, on this axis is the rotation angle of the domain wall. And this is kind of the anisotropy that you have to beat. So you create a double well structure in the system, like you was mentioning yesterday. And with the magnetic field, you can lift this, for example, and then you enhance or decrease the tunneling between the two. And they propose to utilize some higher levels for manipulation. So now, for me, this is not like exactly the qubit story. Is not very important, but it highlights already what they are kind of thinking about. So our question is, why not harnessing, also the magnons in these systems, especially because if you want to do something, like transfer information from one side to the other, they are long wavelength, they are traveling modes, so they are kind of natural for doing any kind of quantum information shuffling between systems, and maybe they can also help you unravel any quantum structure of this level. So as we saw, I will not spend time on this slide because we had these beautiful 2 talks where you can manipulate domain walls with magnons. For example, this is a work from UCLA, the Kang-Wang group, where domain walls and spin waves interact insulating magnets. So spin waves are responsible for motion, so spin waves interact with domain walls. And the question, can these magnons see any of level structure? Also, Schumacher group in Vienna, they create these nanomagnetic devices where basically they create magnonic cavities, and they show that by changing the dimensions of the magnonic cavity, here is Ig, you can really tune the frequency, the resonance frequency of this wavelength. So you can really construct these systems. So the goal in our work, take one of these nano device and the domain wall in it. So that's our system. I'm coming now back to it. We have a domain wall in an insulating wire pinned at position D0, and finite size of the domain wall. Here there is a barrier between this waveguide and the external world where you apply microwave to manipulate. So, and this domain world exhibits some level structure, and if you're lucky, you can define a qubit there. Of course, there are many levels, and that's what I'm really interested here. And that's kind of the level structure. You have the localized domain world, the easy axis anisotropy, and coupling between the domain world and the magnons that I will discuss in the part. So how to describe the evolution of the system. So N is magnetization profile of the domain. And very similar to what Rizzo was mentioning, but I take a much simpler system, just ferromagnet, not ferrimagnets. So it's actually much simpler, but it's applicable to antiferro or ferrimagnet. Of course, we can complicate the problem. So there's the Lagrangian that describes the system. We have the kinetic term, we have the exchange interaction, the different anisotropies, and we apply also the magnetic field in plane. And the dissipation is quantified by this Rayleigh function that accounts for the Gilbert damping in the system. And to make just to simplify our task, we also take this interaction between the cavity here and the external world via tunneling tau. So that's how we envision our total system. So now, first, the isolated domain wall dynamics that goes along very similar to what Rizzo was telling. In the absence of anisotropies and magnetic fields, here is the profile of the domain wall with the topological charge, and you can lump everything into some effective description of the domain wall, accounting for the kinetic part and the potential, which here we assume to be in plane anisotropy plus this magnetic field B tilde, where B tilde it's B over this anisotropy. And the Rayleigh function looks like that. So that's all standard. So in order, we have to decide on what do we want to do with this domain wall. We have this Z and phi, but what we decided is to pin this domain wall at position Z0 by decrease in the easy axis anisotropy at this position, and then if that is strong enough, you can integrate out the motion along Z, and you end up with a particle on the ring where this effective mass emerges. Again, very similar to what Jesus was mentioning, but a bit of different origin of the mass. And so that's our starting Hamiltonian, p squared over 2m plus d phi, extremely simple. Of course, all the energy scales, length scales are lumped into this effective mass that contain details. And if you quantize your momentum, you can write the Schrödinger equation and define the level structure of your system. And that's how it looks. You could have the double well potential depending on the magnetic field that you apply. That's what Rizzo was looking at, this double well potential, and then define a qubit in these lowest two states here. We are more interested in this regime, where, for example, either B or B a bit larger. Here we have an inflection point, so it's a quartic potential, and you can find how the level structure looks like, and epsilon q is the difference between the first and excited state. So that will be the qubit level. So just to give you, so this is exact, while this is using some kind of quasi-classical theory, Bohr quantization, Bohr-Tomorrow quantization to find some scalings. With the domain wall size of n, domain wall is the domain wall, is the size, the number of spins within the domain wall, while delta k is the strength of the pinning potential. So if we look at YIG, give some estimates. Of course, all these parameters can change when you take a small system compared to a bulk system. We find that epsilon q in this system can be 10 or 100 megahertz. It's not bad, it's not great either. But as Jude was saying, it can be faster, for example, for ferrimagnets. So you can get much better. But again, here in this work, we are not interested in getting necessarily good numbers for the cubic. It's a bit of a different range. Now you can also look at dissipation, which is very important when you talk about quantum effects. And the dissipation, usually what you do, you write down a Limlat equation describing your system. Here H phi is the unitary dynamic part, and gamma j k describes the rates from between different levels, j and k in the domain wall. And we describe this through this minimalistic way by just quantizing the Gilbert damping in this form. So we're not interested in doing some microscopic, but that's kind of the way, very similar again to what we're doing. However, we're not focusing only on the two levels, we're focusing on all the levels of the system, of the domain. Still nothing quantum. And now brings me to magnons. And to describe the magnons, I adapted here from very beautiful work by Serko and Oleg here with Yaroslav and Viktor Galitsky, where they describe the fluctuations on top of the domain wall through these variables phi and delta phi, and they introduce this variable delta and 1, the variation in angle theta, and the variation in angle phi. So these are the magnons on top of the domain wall, and they interact with the domain wall via this potential, which, when you write down the Euler-Lagrange equation for this Hamiltonian, for this Lagrangian, you end up with this solution. I'm referring to this work for how these solutions are found using supersymmetric quantum mechanics. So one can write the solutions in this form, and these are like standard wave function of the magnons on top of the domain wall in the infinite system. Now, I want to stress that that's for the infinite system, and that's the spectrum. So the spectrum is gapped, so the magnons are indeed high there. So if you're looking at something that happens at low energy, you might say, magnons have no effect. However, once you put things in a cavity, you need to put some boundaries here, and the boundaries that we use is the spin current doesn't exit at the boundaries. And once you do that, you just solve like a usual particle in a box, but with a bit of a twisted boundary condition, and you can find out the solutions for this problem, which you cannot find exactly, but you can find the Transcendental equation. And because we want to look at the cavity, we want to see, okay, how does the eigenvectors associated with this cavity look like? And L is expressed in terms of the domain wall size. So we are interested when L is much larger than the domain wall size. And here, what's just as an amusement, maybe is known, maybe not. What an amusement is that if you pin your domain wall, so if you pin your domain wall, or if you don't pin your domain wall, the spectrum of your spin wave cannot remain the same, which it's very different from like a particle in a box. So if you pin a domain, if you put a delta function in a potential wall, you put a delta function in the middle, it breaks the system in two. So basically you get two decoupled systems. That doesn't happen for this case. So you see here, you get basically the same with strong isotropy or without, you get the same k vectors. And then just, as amusement, it boils down to this expression of the wave function compared to the usual particle in the box. So we can find that, what are the eigenmodes, and now once we are equipped with that, we can start and let the domain wall fluctuate. So until now, this was over a static domain wall, and once you let it fluctuate, also again, second with Oleg and Yaroslav and Viktor Galitsky, they found that you get two types of interactions, even at the level of the very phase term, basically there is one term, phi dot, that couples to the magnons and one to the motion. But because it's spin, we forget about this. So this is nothing but solving the problem in the rotating frame, and the magnons just act as some effective magnetic field on the domain wall. So that's what this term tells you about. So you can find the momentum associated with this term, and okay, you find here some PNM that is given by some integrals there, and these are the amplitude of the magnet. So that's our construction. And finally, you switch to Hamiltonian, and that's our Hamiltonian. So the Hamiltonian, to start with, that describes the interaction between the two systems, doesn't couple. Well, it has also some terms that couple at the level of the Hamiltonian part in the Lagrangian, but it basically mostly couples via these very phase terms that enters here and modifies the p phi, like adds a gauge field. So that's our starting Hamiltonian. That's our first, kind of main result. The coupling between the degrees of freedom of the domain wall and the magnons, they occur via this term. So if you expand, it's p phi times pn. That's our coupling. It occurs via the very phase induced by the magnons when the domain wall precesses. Nevertheless, if you quantize, you get, instead of here conjugate, you get dagger, but the magnons are still high. So whatever you do, if temperature is low and there are no magnons there, this term, you have it there in the Hamiltonian, but is not very effective. So can we even see this, interactions if the energy separation is huge? And naturally, no, but looking more into the literature, there are systems where that occurs, and that's called cavity optomechanics, where you look at interactions between nanobeams that are immersed in a cavity, optical cavity. And there also you have the nanobeam energies are very low compared to the frequency of the electromagnetic field. However, what you do, you drive the optomechanical cavity to bring in resonance with the nanobeam. So that's what we also propose based on optomechanics language to drive one of the magnons, say the n magnon, close to the resonance. So omega n is the driving frequency, and this driving frequency is close to epsilon j, the difference between the actual magnon frequency and the driving frequency is close to some energy separation in the domain wall. If you do so, you start populating coherently this magnon mode, which gives it population, a classical part alpha n plus some quantum fluctuations on top. So that's what optomechanics or cavity optomechanics people do, and we realize that applies also to us. So we are able to map our problem to a cavity optomechanics, where we find this interaction here, Gn, that is controlled by the Berry phase, which is given by some integrals of the magnon wave function over the domain wall, times the alpha n, the amplitude of the cavity, the magnon in mode n, which can be controlled by how much power you put in your system and the effective mass. And now delta n is comparable to the energy splittings there. So that's how we start. And we also have to set up some, what we want to do. So you can do many things with this Hamiltonian, but for this talk, I will focus on some energy scales. So I need to assume some energy scales. So first of all, I assume that kappa n, the decay of the magnon, it's much smaller than basically the coupling strength G. So much larger, sorry, than coupling strength G. Maybe the magnon decays much faster than this. And that allows us to eliminate adiabatically the magnon, so it has some reason. Kappa n, however, it's smaller than the level spacing in the domain wall, so which allows for efficient back action and cooling, as you will see in a moment. The Gilbert damping rates are smaller than the induced rates by the coupling to the magnons, which allows to do something actively with these magnons on the domain wall that beats the Gilbert damping. And also that the magnon spectrum is well resolved. So the magnons travel quite a few times between the two ends of the wire before it decays. So then once these are in place, you can write down the full density matrix for your system, which is the way to describe the quantum dynamics. Again, we have some Lindblad kind of form for the density matrix. Now we have the magnons here, and Hn is the Hamiltonian for this that I showed in the previous slide. So it's this thing. So you have that, again, that's kind of normal in the cavity optomechanics. What you do, you integrate out these degrees of freedom, and what you end up with is the density matrix that describes only the domain wall itself. And what are the differences compared to its, say, isolated dynamics in the presence of Gilbert damping is that now the magnons introduce these rates here, and also it shifts a bit the energy. And these rates are very important because by tuning delta n, you can, in principle, make this delta n equal to this. You can decrease gamma jk or enhance compared to different transitions. So you can really tune the transitions and specific transition between the domain wall levels, and you will see how that can help you. So what can you do with that? So now, we introduce kind of the machinery, and now can we actually, start doing something useful? So first of all, in the stationary state, we find that rho phi is diagonal in the domain wall states, where Pn are the highly non-equilibrium population of the domain wall level. So now I'm not talking only about the qubit, like she was mentioning, but I'm talking about all the levels. And we have the thermal rates that gave Jisoo his T1 and T2, but here between all the levels, and we also have this magnon-induced rates that we can manipulate because of the coupling between the two systems. So if delta n equals minus epsilon 1, 0, you can increase drastically the rate between the first excited level and the ground state, and you can beat the Gilbert damping, at least in the limits of the scale that I was mentioning, which should allow you to initialize the qubit state. So let's see how that works. So here again, some parameters with some Gilbert damping and how the thermal distribution looks. Temperature here basically is chosen such that T is larger than the level spacing, than the average level spacing. So get a boring thermal distribution. Here, you cannot really initialize, you should cool off in order to initialize the ground state, you should really cool off the system even more, but maybe I don't have the possibility. However, if you now drive your magnon, and here I didn't optimize anything, I just basically put some parameters in and see what happens. And even with this non-optimization, we get like population almost 1 in the ground state. So that will constitute, initialization of the qubit in Jisoo, for example, so on, right? So that's how, in principle, I initialize, and then I take the driving out, and then I have to do something over the time scale of the qubit decoheres, right? I can start manipulating and play with this. So the fidelity here is like 90, I think 91%, but by optimizing, you can go even higher. So that's the ground state cooling. However, it's not really yet quantum, it's just, preparing in the ground state. But now let's try to do something more quantum. Yeah. Mm-hmm.
So, what's it? Which kind of magnon drive? So you apply microwave.
You apply microwave, and if the energy splitting is smaller or larger than this delta, if delta n becomes negative, the magnons basically take energy out because you invert. It's like making the magnon energy, make the magnon negative with respect to the transition. So that's how they use this, side band cooling, for example. So and then so you can just extract energy from your system. So now let's look at the opposite effect where, for example, gamma, here I put epsilon jk, more general, where the upper rate is much larger than the lower rate. And in particular, if this is delta n equal epsilon 1, 0. So, and again, the stationary state is the same, and we need some measure to define quantums. And one measure that in the literature, at least of quantum optics, is the Wigner function. This Wigner function, it's in the classical physics we describe the distribution, the probability distribution in the phase space, and that's always positive. However, in the quantum regime, defined like that, can be also negative, and when that is negative, it doesn't have any resemblance to a probability, right? So it means, by definition, that the system became quantum. So that's our measure of quantumness. So if you have some quantity that classically has to be larger than 1, and if you go quantum, can be below 1. If you prove that it's below, you reach some quantum state. And more importantly, if you look, so that's of phi and p phi, if you look at the origin here, it's given by this expression. So n runs from 0 to all the states with -1 and to Pn. So let's see. Again, for the boring thermal state, of course, the Wigner function is almost 1. And what we find is if you drive between 1 and 0, we get a Wigner function that is minus. So we get a negative Wigner function, which signals that your state here, even though it's there's nothing entangled there, but it still has a quantum nature. So the thing is not much smaller than 0, but it's smaller than 0. And here again, I didn't optimize kind of the parameter is such that I get even better. So if you optimize, in principle, you can make this fidelity of initialization in the second state, which would mean in the qubit story would mean initializing the system in the 1 state even higher. So that's how you prepare. But of course, that's just preparation, right? So it's still nice because you can connect now this population, you could connect it directly to some measure, right? So that's nice. However, in the end, you still want to measure something, right? So as a measurement, usually when you think of quantumness, you think of some kind of correlation, right? Some G or some second order coherence function and so on. However, here we're proposing to look not at that, but just power, right? That's the simplest way to measure something. You just look at the power emitted. So what we say, okay, let's prepare the system, or let's assume that Gizu did an operation and we put the qubit up. Right? Let's assume that we put the qubit up. And now the idea, again, the idea from cavity optomechanics is to drive the second mode, for example. Let's say N is the first magnon mode, the uniform mode, and P is the second mode. And you can do it if they are well separated. So if you drive at resonance this mode, and now you want to see how the magnons emitted look like. And you want to see how magnons emitted look like around this omega P. So what we looked at is the power spectrum, something that you measure, right? And utilizing what in quantum optics people talk about is input-output relations. Here I kind of, I changed the measurement side. Of course, you can do everything on this side, but just for pictorial, I separated the two ends. So what you want to end up with that S of omega looks like this around omega P. There is a huge peak at omega P also, the fact that the magnons are emitted at omega P also, but there are also side peaks at omega, omega equal omega P plus these guys. And if you also, this total rates, I'm not going to go into details, but it's just related to the Gilbert damping plus this extra induced magnon damping. What's important for this rate is gamma nk equals gamma kn here. And if you take the rates, the ratio of the amplitudes the heights of the peaks at omega L plus epsilon j k. Sorry, it should be omega p. Sorry, should be omega p here plus epsilon j k and omega p minus epsilon j k. It gives you direct access to the populations. And indeed, to do that around omega p, you get indeed the peaks, and that once you measure the population, you can reconstruct your Wigner function, and experimentally that will be experimentally, but would be a way to determine the Wigner function and eventually determine the quantumness of the system. Of course, you can also go further. Once you determine the quantumness and so on, you can do also qubit kind of implementation. You can utilize this to create entanglement between different domain walls in the same wire. They don't have to be close to each other. The magnons, they should just be they should just be in the magnonic cavity. They should not be in proximity to each other. And because it's driven, you have to drive the system. You can control it by just stopping the driving. So you can control the exchange interaction for the times that you want by just controlling. Okay, so these are my conclusions. We find some domain magnet interaction omitted by the Berry phase terms, but turns out that if you take the Hamiltonian contributions, they give you the same parametric dependence, so nothing much changes. Driving the magnons can manipulate the domain wall populations, which in turn can be measured and can give rise to non-classical states. So we characterize these non-classical states by the Wigner function. So a quantity that in classical physics, it's always positive. And we find some instances where this is negative, which in our view, that's a proof of quantumness. And yeah, that's the detection in the power spectrum. Of course, you can go much further. You can explore the strong coupling regime, where these two guys start to hybridize strongly, and you can find some chains coming and even more quantum effects. Antiferromagnets and ferrimagnets, I think they exhibit much better energy scales. Magnostatistics, that's another thing that one could look at, what the magnons is emitted by this automatically driven system. More complicated objects, like Christina was talking about skyrmions. So in the end, also there you have to prove the quantumness, so maybe it can be applied there, and maybe even interplay with other degrees of freedom, like superconductivity. Okay, thank you.
Thanks to Mircea for the very interesting talk. And now it's time for questions and comments.
There's just two quick questions. First one is, at the experimental, always a question at what size is the changeover from the quantum dominated to the classical dominated regime?
Yeah, so it should be that the levels, the domain wall levels, beat their width, exactly their line width. That's all. Yeah.
Well, that's all that can be challenged.
That can, okay. Yeah. No. But also, so here we also show that we can manipulate the rates, right? So in principle, maybe you can do something about it.
And second question, magnons itself are bad as qubits because it's open system. So in your case now, did you also discuss moving the main wall, like flying qubits, or this is stretched?
This is that it's pinned, and the magnon just on top. And yeah, we don't use them coherently, the magnons here.
Let's make it.
Same problem.
Yeah.
Yeah.
So when you say entangling two domain wall in the cavity, and what's the typical distance you expect?
It's as long if the levels are well, if the Gilbert damping of the magnon is larger than the separation between the magnon levels, then it's just basic. You can do it over the whole cavity, right? Because that gives you the length scale that the magnons see. If the line width becomes larger, then that will give you, right, is the length over which they decay. Right? So, sorry.
Can you implement interpolation
I think it should be possible. It should be because once you write, I mean, we just look at this dissipative dynamics in this energy, but this Hamiltonian, this is that's generic. Then what you do afterwards, you will look at really at cooling and this kind. But if you look at this, then you can plug in magnon, and of course, I mean, these magnons can couple to this P, right? That you project in the qubit basis and stuff, so you can start manipulating coherently. Until now, I did mostly incoherent.
Yeah, any other questions or comments? Yeah, so I actually have a follow-up question from what Segon just asked. So, I mean, how stable is this? I mean, if you suppose you realize this kind of quantum gauge, how, and certainly this is a quantum gauge where this magnon cavity plays a big role. And suppose we change the magnon mode, modify the magnon modes by saying, somehow modifying the boundary conditional rule, how is that going to actually affect the stability of these quantum gates?
Yeah, so first of all, so here, what we talk about magnons that have lifetime smaller than the distance between the magnon modes. So then one can address them separately. So in that case, it goes back to kind of, how cavity QED looks like. And, one can just take the same kind of language from manipulation via photons and stuff like that. But if the cavity becomes larger, such that the line width becomes comparable to the level splitting of the magnons, then I don't know exactly, how to deal with that, to become a bit of a mess. So I don't know what would be coherent, because if it's too far, the magnons that you inject here to manipulate them, maybe they don't even reach the domain work, right? Because they just decay by the time they are the domain work. Maybe they don't have any phase coherence. So one has to look at these length scales a bit. Yeah.
But that's all something issues that arise only when you have like finite change in these parameters.
Yeah.
Okay. Other questions or comments? Yeah, then let's thank Mircea again